Hello and welcome Chem 51. This is week 3 lecture and it covers sections 1.4 and all of chapter 2 in McMurray as well as activity 24A in the lab manual. So if you read those before watching this lecture, you'll get the most out of it. So to begin, the symbols for each element on the periodic table they mostly represent their English names, but some of them come from their old Latin names. So let's take a look at that for a second. You do have a periodic table in the front of your book. This is also ptable.com. It's very nice. If you look at the upper left-hand corner, I can select a particular element and it will give me all of the information. So one example here is lithium. The English word lithium, it's Li. But Na represents the Latin name for sodium. So same thing with potassium here. So that's something we need to watch out for. So it's unnecessary to memorize the entire periodic table. You'll always have access to a periodic table in this course, even during exams. But it is helpful to know the common and relevant elements. And those ones are listed in tables 1.2, 1.3, and 1.4 in pages 8 through 9 of McMurray. So it's mainly the ones on the first few rows of the periodic table. So atomic theory and the structure of atoms. So an atom, oh, I lost my pencil, there it is. It's the smallest and simplest. The smallest and simplest particle of an element. So it means indivisible. It was originally thought to be the smallest unit of matter, but now we know that atoms are made of smaller subatomic particles. So let's draw a picture of that. One subatomic particle is a proton. We'll symbolize it with a plus sign there. And a proton symbol is just a lowercase p, or sometimes you'll see p plus to indicate the charge. And so this is a very small particle. The mass is 1.67 times 10 to the negative 24 grams, very tiny, or 1.01 AMU, which is an atomic mass unit. We also have another subatomic particle, the neutron. I'm just going to put a 0 in that. Oh, and another thing to say about the proton is a +1 charge. Okay, so this neutron and that is given either just an N or an N with a 0 up top. You'll see both of those depending upon the textbook you're using. The mass is, to this many significant figures anyway, also 1.67 times 10 to the negative 24 grams, or 1.01 AMU. Now, if we went farther past the decimal on these numbers, the proton and the neutron would actually have a different mass, a very slightly different mass. Okay, so all the way out here, there is an electron. Oh, another thing we should say about the neutron is no charge. And the electron, that is symbolized just like we put it right there, putting it in a circle just for the purpose of the drawing. But what's happening is this electron is whizzing about around what we call the nucleus of the atom. Okay, so the mass of an electron is super tiny. It is 9.11 times 10 to the negative 28 grams, or 5.49 times 10 to the negative 4 AMU. An electron is so light that we consider it to be massless. We just consider it to not weigh anything. Okay, and its charge is -1. Okay, so an atom, if it's going to be neutral, is always going to have the same number of protons and electrons. If you have an imbalance between the two, it's called an ion. It's a charged atom. So protons and neutrons are held together in the nucleus, the center of the atom, and the electrons are moving randomly. It used to be thought that they went in a circle around the nucleus, but it's really random. And there are areas where an electron is more likely to be found, but there's actually a probability that they can be found anywhere in the universe. That means parts of you, all of your electrons, could be anywhere in the universe. There's a slight chance, anyway. So, elements and the atomic number. So, the atomic number is symbolized by a capital Z, and it represents the number of protons in the atom. And so the number of protons identifies the atom. Or I should even say it defines the atom. So a carbon atom will always have 6 electrons. Oh, excuse me, protons. If it's neutral, it'll also have 6 electrons. And so the number of neutrons, however, that can vary between individual atoms of the same type. So there's the mass number, which is symbolized by A, and that's the number of protons and neutrons added up. And we'll see momentarily that since different atoms can have different numbers of neutrons, then different atoms of the same type can have a different mass. And so the number of electrons we did not include because they weigh so little, as we mentioned before. Okay, it's insignificant how much they weigh. So, for example, one way to symbolize the element is we would say X, A, Z, where X equals the symbol from the periodic table. Okay, so let's look at carbon 12. So that would mean we call we just call it carbon 12. And the 12 symbolizes the atomic mass. So that would be a big C with a 12 up here and a 6 down here. 6 being the number of protons and 12 being the atomic mass. So given this knowledge, we should be able to fill in this table from incomplete data. So let's look at the first two columns. So since we know the number of protons defines the identity of the atom, we can look these up fairly quickly on the periodic table. So for iron, Fe, okay, the number of protons, let's check on the periodic table. Iron here is number 26, so that means it has 26 protons. Okay, now iron 2 plus, that is an iron ion, so it is missing 2 electrons. It has 2 more protons, more positively charged atoms than it does negatively charged atoms. But it's still iron, so it's going to have 26 protons. Okay, now let's look for what has 10 protons and what has 11 protons. We can look for those at once. So looking for number 10 is neon, and number 11 is sodium. Okay. Then this W here, that's another one with the Latin name. It's tungsten. And that's actually all the way down here. That's number 74. So we have 74 protons. Okay. So now let's go. We've identified all of our elements or ions. And so let's go line by line now. So for iron, we have 26 protons and 30 neutrons. And so that's going to give us a mass of 56. Okay. For the number of electrons, I'm going to notice that iron is neutral in this first row. So I'm going to have that number match my number of protons. In the second row, however, the iron 2 plus, it's going to have the same mass, of course. It has the same protons and neutrons, but it's only going to have 24 electrons. It has to have that imbalance between protons and electrons to have that 2 plus charge. Okay. In the third line with neon, I'm given the mass of 20. So if I have 10 protons, that means I must have 10 neutrons as well. So what I'm going to notice for sodium is that there's actually an imbalance. I only have 10 electrons for every 11 protons. So I actually have to give this symbol a plus charge. I wasn't quite finished with that one. Okay. So finally down to tungsten, 184, the mass, minus 74 would be 110 neutrons. Okay, you may notice that this has a huge amount more neutrons than protons, and it's very different from, say, iron that has just a small difference. As you go lower in the periodic table, you end up with that pattern of having more and more neutrons, and those are needed to stabilize the protons sticking together. Okay. So last thing, I'm going to notice that my tungsten is neutral. So that means I must have 74 electrons to balance out the protons. So these different versions of these atoms are called isotopes. Okay. So the number of proton defines an atom's identity. The number of neutrons, oop, I spelled it wrong. I'm going to erase that. My bad. So the number of neutrons can vary among different atoms of the same type, of the same elements. So previously we looked at carbon and we specified carbon 12. Carbon 12 is an isotope of carbon. It's the one that has 6 neutrons and thus a mass number of 12. But there is also carbon 13 and carbon 14 that are less abundant. Okay, isotopes. So these isotopes have the same atomic number, but different atomic mass. Okay, and included in this example that I just spoiled for you a moment ago, these numbers are representing the atomic masses of these different isotopes of carbon. So we would just draw them symbolically like this. We already drew that one above. That's how we would do that. So the average atomic mass is calculated using the relative abundances. It's the relative abundance of different isotopes, and that's expressed as a percentage. Okay, so let's fill in this table together. So we've got carbon 12, so that's 12 AMUs, and its abundance is 99%. Okay, most of its carbon 12, it's very stable. So its contribution to the average is going to be 11.88 AMUs. Carbon 13, 13 AMU, is about 1%. And so that represents 0.12 AMUs. Carbon 14 you guessed it, is 14 AMUs. And there's so little of it we consider it insignificant, but it's still something. So that is going to make our average atomic mass 12.01 AMUs. Okay, so let's look back at the periodic table for another moment, and we'll tell you the story of how it came to be. So this table is arranged in according to the behavior of atoms. Um, Different columns behave in different ways. And so what happened was this modern periodic table was thought up in a dream by Dmitri Mendeleev. So all of the previous versions had the same goal of grouping the elements based on the behavior, but they were never able to get all of the patterns right at once, whether it was if reactivity was lined up, then the mass would be off, etc. So inspired by the notion that not all elements had been discovered yet, Mendeleev dreamt about a periodic table that has holes in it for all of the undiscovered elements. And we know that that dream was accurate because every element that we've discovered so far has fit into the appropriate hole that Mendeleev dreamt about. Let's go back to our notes. Okay, so what information does the periodic table contain? It contains three major relevant pieces of information. It contains more than that, but we're going to look at these three at first. So it gives us the atomic number. We always want to be able to know that. It gives us the average atomic mass. Okay, and it tells us the symbol. Okay, and you need to note that the symbol is case sensitive. First letter is always capital, second letter is always lowercase. So, so a typical tile on a periodic table would have our symbol in the middle. Most of them don't have the names. The one that we've been looking at has the names and a whole lot more information. But here's what you're most likely going to see on a typical periodic table. There's our atomic number. There's our symbol. And there's our average atomic mass. So what are some different characteristics of these groups on the periodic table? So let's write this down and then we'll take a look. Or maybe we'll flip back and forth. So on the left side of the periodic table are the metals. Yes, let's flip back and forth. So everything from zinc to potassium, all the way up and down, and even under this staircase um, are metals. Okay, there's a lot of metals. Okay, and on the right, above the staircase, we have nonmetals. It's above the staircase on the right. So pretty much everything that's in green here is a non-metal, as well as these purple ones. But these purple ones are, we don't really worry about them because they don't really react. But they are technically non-metals. Everything on this side of the this blue staircase, or this staircase of blue elements. Okay, and those blue elements that form the staircase, that small number of elements are metalloids. They do weird stuff. So the metals are split into two groups. There are so many of them, but we have two distinct characteristics between these groups. There's the main groups, and those consist of the first two columns. Okay, and then there are transition metals, which are those 10 columns in the middle, all of the ones in pink, from scandium to zinc. These are our transition metals. And then over here, hydrogen can act like a metal. It's not really a metal, but it acts like one a lot of the time. But lithium, beryllium, these are our main group metals. And we'll get into more details about why they're separated later on. Okay, now let's talk about the electronic structure of atoms. So we know that atoms have electrons that are moving randomly. They're moving randomly around the nucleus, but there are certain regions where the electron is more likely to be found. And we can describe those with varying levels of specificity. So the first and most general location of electrons is called the shell. And that is symbolized with the letter N. And the, the shell, the letter N represents different layers of electrons around the nucleus. So let's draw a quick diagram. Let's say I have one proton here. So here's my first layer. And then I have different layers on top of that. Looks like we only have room for two layers. Okay. So n equals 1 is lowest in energy. Because it's closest to the nucleus. Okay, so the electron can exist in any of these layers, but it's typically not found in between the layers, in between these shells. Okay, the second and slightly more specific location of the electrons is called a subshell. Okay, and that's a region of space that each shell is divided into. Okay, there's a region for each subshell. So these subshells are designated by the letters S, P, D, and F. Okay. So the third and the most specific location of the electrons are regions of space within the subshells. Okay, and those are called orbitals. Okay, each orbital can only contain two electrons. Okay, so I want you to see table 2.2 on page 57 of McMurray, and you can see the number of electrons within each designation. So what does that look like? So I'm drawing a Cartesian plane, trying to draw it three-dimensional. And here's an s orbital. Okay, and it's spherical. Okay, so this is called the s subshell, and it only has one orbital in it, the s orbital. So let's look at a p orbital, or I should say a set of p orbitals. So these are dumbbell shaped, and they exist along the axes of this Cartesian plane. Okay, so these are three p orbitals. There's px, py, and pz. Okay, dumbbell shaped. So each of these three orbitals can have two electrons in it. Okay, now let's look at electron configurations and orbital diagrams. Okay, so in electron configuration, an electron configuration is a way of describing the location of all electrons in an atom very specifically. Um, we should say the most likely location because this is all based on probability, but we can kind of think of it in this class as definitely the location. Now, we have three rules that we have to deal with when we're creating an orbital diagram or an electron configuration. So the first one is the Aufbau principle. Had to check to make sure I was spelling that right. And so it states that orbitals of the lowest energy will fill first, and they will build up from there. See, this is also called the building up principle, and I'll show you in an example in a moment. So it states that an orbital of a lower energy or a set of orbitals is going to fill up completely before moving on to the next shell, or we could call the next energy level. The second rule is called the Pauli exclusion principle. And it states that only two electrons can occupy an orbital, and they must have opposite spins. These are not literal spins, but we can think of them that way. We consider spin up and spin down. And so finally, Hund's rule. Hund's rule states that orbitals of the same energy will be half filled before the electrons start pairing up. And we'll see an example of that now. So we're going to make the orbital diagram and electron configuration for selenium. So let's look at that on the periodic table for just a second. So selenium is number 34. It's a nonmetal. And so it's going to have a neutral selenium is going to have 34 electrons. So let's start filling from the bottom, lowest energy. Okay, that's an electron, and that's an electron with the opposite spin. Okay, so what did we say it was? 34. Now I won't forget. So there is my 1s. In the energy level of 1, it only has one s orbital. It's too small to fit any other orbitals. So we'll go up to n equals 2 to the 2s, and we'll put 2 electrons in there. And then for the 2p, we have those 3 dumbbell-shaped lobes. And so I'm going to fill each one with a spin up electron before I add any spin down electrons. Okay, fill that up. Fill up the 3s. Same thing with the 3p. And the 4s. What's this though? The 3d. What happened there? Why isn't the 3d here somewhere? Um, it just has a little bit higher energy. The 4s is a little more stable than the 3d, so the 3d lies higher in energy, and you'll see that pattern continue as you go higher. So let's fill up the 3d. How many electrons do we have? We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So we get 4 more. So this finally the 4p, and we have 2 unpaired electrons. So this is the orbital diagram. We'll put highest energy right here. And we just built it up. And we do it the same way for every element. So what does the electron configuration look like? So I'm just going to list out how many electrons are in each one. So I'm going to say 1s, 2. That 2 stands for number of electrons. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then 4p4. That is our electron configuration. Okay, so now we know where all of the atoms are, or excuse me, all of the electrons are in this one atom. Okay, so let's talk about electron configurations and the periodic table. So there must be some sort of pattern on the periodic table, right? So let's look on page 62 in McMurray and see figure 2.7. And you'll see that the periodic table is split into blocks. Okay, you'll see the S block in the first two columns, the D block in the transition metal valley, the P block of the nonmetals. And so what this is describing is the location of the outermost electrons. And those are known as the valence electrons. Okay, valence electrons are always the highest in the highest energy S and P orbitals. Okay, and so the order of the elements on the periodic table by atomic number will represent the filling order of the orbitals. Okay, so elements of the same group, and by group, I do mean column on the periodic table. Get used to calling them groups. Okay, so elements of the same group on the periodic table are going to have the same number of valence electrons. Okay, and they'll be in the same arrangement. So it was kind of a pain to write all of this out, right? For an electron configuration. Why don't we shorten it a little? So what I'm going to do to shorten this is I'm going to state the previous noble gas, and then fill the orbitals after that to the highest energy level. What's a noble gas? Noble gas is this last column, column 18 on the periodic table. Helium is the first one, the lightest one. And these noble gases are not reactive at all, really. You have to put them under some extreme artificial conditions to get them to do anything. So let's look at the shortened version of the electron configuration for selenium. Okay, just like we did before. Argon is the previous noble gas. We'll look at that on the periodic table in a second. Actually, let's look at it now. So argon, selenium's right here in n equals 4, the fourth row. Argon is the previous noble gas at the end of n equals 3. So we've got argon, 4s2, 3d10, and 4p4. Okay, that's a much better way to write it out. So the final topic we have for this lecture is electron dot symbols. And electron dot symbols are a preview for what we will be doing in the very near future, which is Lewis dot structures. But for now, we're just going to do electron dot symbols. Okay, so those can be used to represent the valence electrons of a particular atom. So I'd like you to turn your attention to table 2.5 on page 65 of McMurray. And what you're going to see is the valence electron pattern, the electron dot symbol of the first elements in the periodic table, the first few rows. Um, so for selenium, let's look at our orbital diagram here. So our valence electrons are 4s and 4p, not the 3d. And so we are going to note the fact that I have a couple of pairs, and then a couple individual electrons. So I'm going to represent that in my electron dot symbol. So note the paired and unpaired electrons. So I've got the two pairs, so I'll draw those like this, and then I have my two on the outside there, my two lonely electrons. So that's an accurate way to represent the valence electrons for our purposes at this point. So that concludes week 3 lecture for Chem 51. This should prepare you for the next activity, which was activity 24A. I encourage you to look at the book again and review what you read before the lecture to see how much better you understand the material before you come into the in-person portion. All right, thank you so much for your attention.